That working? All right. Okay, so yeah, thank you everyone. Thank you for inviting me and creating this, and great to see everyone coming to Australia for once. So yay. I'm Andy Perfors. I'll be talking about human induction and large language models. But I should sort of preface this by saying that the bulk of this work was done by Jerome, and I don't know why this is sort of covering someone's head. Hang on a second. Let me try it again. All right. So most of this work was done by Jerome and Charles and Keith as well. Jerome is not here. He's in fact not even a PhD student yet, but he'll be starting at Stanford. So keep your eye open for him. He's pretty amazing. And also, if you want all the details, it's just come out in cognitive systems research. So yeah, so is there a way to get rid of this little top thing? This is really irritating. Yeah, yeah. Oh, and view. Yeah, okay, sorry guys. All right, fantastic, okay. All right, sorry. So yeah, you got to start a talk like this with some funny thing, right? And so I don't know if you saw this recent BuzzFeed that came around, but someone asked these models to sort of create pictures of what Europeans think Americans look like. As someone from Colorado and New Mexico originally, I found these very, very funny. There were some other really great ones. And then in honor of our organizers, there's New Jersey and California in there as well. Obviously, this isn't a pure language model because it's, tapped into the image generation one. But even if you just look at ChatGPT, so this is, my 7-year-old, I gave him ChatGPT to babysit him while I had to tidy. This is one of the questions he asked. He sort of, he's basically teaching it his new language. He's got really weird words in his language. Means I'm a glow-in-the-dark red chicken, and he's saying use these in a sentence. And indeed, ChatGPT comes up with fairly sensible sentence, right? And clearly, glow-in-the-dark red chicken was probably not in its training data, right? And so there's, we've all seen anecdotal examples like that. And it's, it's very easy, I think, to sort of get absorbed in the wow factor or get in an endless effort to find something that it screws up on, and sort of, and that makes it, both of those things make it kind of hard to look at the real strengths and weaknesses. So what we're trying to do is study it in a more systematic way, much as the previous talk did here, using tests that we really know a lot about how humans reason, that we think are at the heart of some of human intelligence. And so that test is induction, which I think is arguably, analogy is a kind of induction, but, generalizing beyond a little bit of data. That is probably, I think, one of the things that humans do best. Although sometimes that goes awry too. We sometimes don't want to generalize too far, but we know not to, right? At least in this case. So we particularly looking at category-based induction, which probably most people here know, but I'm going to sort of quickly, remind you of the salient bits. So in category-based induction, the idea is you give people sort of some premise categories and say they've got some property. I have no idea if this property is true. For all our things in our experiment, we just said property P, but it's more exciting to have an actual property over there. So you've got, say, you give some premises and then there's some conclusion, right? So if robins and blue jays both have this, what are the odds that sparrows do? Right, it's not deductive, it's probabilistic. And you can compare the strength of arguments like this, where sparrows is actually quite similar to robins and blue jays, to one where the conclusion is, say, very different, right? And so this is one very, very well-attested effect where almost everybody will say, hey, the one where the conclusion is very similar, that's a stronger argument than the one where the conclusion is different, okay? So that's one very, very well-replicated category-based induction effect, but there's lots of different phenomena. And I'm gonna sort of go through a few of them. In this paper, we actually looked at all of them. Don't have time for all of that. But as we kind of went through, I found myself kind of mentally sort of chunking the phenomena in terms of what they kind of reflected. So And again, I'm massively generalizing. Sorry for the category-based induction here, people, because I'm totally, screwing up all the nuance. But we've got some phenomena that I think sort of largely kind of reflects something about the representation, right? So things like stronger arguments go to more similar conclusions, or there's stronger arguments if the premise is very typical, and those are basically, you can get these right if you have something kind of like the same representational space. So you've got a representation of similarity. And then there's a number of things that require that, but that I think require something a little bit more. And so these are things like premise monotonicity, which is essentially saying most of the time, the more premises you have, the stronger the argument is. Or diversity, which is the more diverse the arguments are. That is, the more different kinds of things you have as premises, the stronger the argument. And so that's something about the representation, but you also need to have some sort of notions of coverage or whatever. And again, I'm now reprising like decades old cognitive science, so apologies, and then there's also this interesting set of things, which are non-monotonicity, which seem to incorporate something additional beyond that. And I think about it in terms of sampling. You've got theories of how the data were generated. The idea of you're looking for things that are relevant is the same intuitive notion, right? You're sort of, what's relevant is, how is it generated with respect to whatever you're trying to do. And just to sort of give a real sense of what I mean by that, because I'm going to really come around to this later. So if you can think of an induction problem, the world, you've got a bunch of things, they've got some property or not. You have hypotheses about that. I had to work Bayes' rule in here because that's me, right? And you sort of figure out how to generalize that according to Bayes' rule. But how far to generalize really depends on your critical assumptions of the likelihood. That is how the data were generated in the first place. And if you assume something like strong sampling or pedagogical sampling, something where like essentially the items are chosen from the concept itself, then what that means is, say you see a polar bear, that's one premise, and then you see a grizzly bear, that's another premise, and then you see a brown bear, that's another premise, except I might have mislabeled those, I don't know bears. But if you see these three premises, you're going to conclude it's probably a bear, right? You're not going to conclude it's all mammals or something like that. And this is non-monotonicity, because remember, monotonicity was more premises make you sort of make an argument stronger. But in this case, if you had more premises, it would make an argument like all mammals weaker, right? And so that sort of notion of the generative process is what licenses non-monotonic reasoning. Whereas if you have a different kind of generative process, which is says, oh, they're sampled without respect to trying to sort of, the concept underlyingly, then you can see the exact same data and it will mean something different. So just very quickly, we've actually done some work showing that, that's what happens. So if you compare arguments like the targets, where you'd predict non-monotonic reasoning, if the generative assumption is strong sampling, versus a control where it should be monotonic either way, that's what you get out of a model that has these different generative assumptions. And that's what you get out of people if you tell them the different assumptions, right? So again, that's not the really topic of this talk, but hopefully by the end, you'll see why I spent so much time talking about this. You can probably guess. What we did is we wanted to look at all of these inductive phenomena and see how well do LLMs do at them. And there's two at the bottom that I've grayed out, mainly because I just don't have time to talk about them, and I'm not sure what to make of them. You can look at the paper if you care, but there's a bunch of others. And again, they kind of reflect different things. And the nice thing is that you can essentially get a heck of a lot of human data on this. There's already been a lot, but we decided to go and make our own gold standard kind of benchmark data set, basically because we wanted everything to be identical except for, the phenomena and so forth. We also found that a lot of the things in the literature, of course, they're looking at one thing and they have their own tweaks on it and everything, and we wanted to get rid of that. And we also did it within 3 domains because we thought, this might be something very interestingly different, both with how humans reason because of our knowledge in different domains is different, and also large language models because the amount of data and the nature of the data in different domains might be separate. So not to go into too many details about the experiments, but these were sort of, pretty intense experiments, not for the people involved. It's the standard kind of experiment. You give people arguments and you say, hey, which one is stronger? But what we did is, given all of these phenomena and all of these mammals, we essentially sampled, that creates many, many more trials than any one human would want to do. So everybody saw a subset of them, counterbalanced and blah, blah, blah. I can tell you about that, but just trust us, there's lots of counterbalancing and everything. But everyone saw some examples of all of that. And then we wanted to do the exact same thing with GPT-2, like literally give it the exact same phenomena and exact same examples. And of course, as we saw with even some of the questions last time with GPT-4, a lot depends on how you ask, right? And so we also we being Jerome, did a lot of tweaking of the prompt. So what I've shown here is the final prompt, the one that did best. By did best, I mean most closely matched the human judgments. But what we did is there were 5 bits of them, both the you might think of it as the introduction, one is the explanation of the thing, one is the presentation of the arguments, the question and blah, blah, blah. And we didn't systematically try all of those because that gets incredibly expensive, but why is that happening? Yeah, but we systematically evaluated them to some extent, right? And so we have different possible things of all of those, and then basically tried a number of them, and this was the best prompt, okay? And for GPT-3, we did the same thing. Actually, the development of this is first we did everything with GPT-3, and then GPT-4 was invented, and we were like, crap. And we did GPT-4, and then went back and used the best prompt from GPT-4, changed slightly so it fit in the length of the API and stuff. Now, the nice thing about GPT-3 is it gives you token probabilities instead of a discrete response. And GPT-4, we actually tried with different temperatures, but it pretty much always gave the same response all the time. So there's just discrete responses to go with GPT-4. All right, so here's the interesting thing. Let's do the comparison. And I'm going to show you a bunch of graphs. They're kind of complicated, so I'm going to try to walk you through. So basically, the columns are the different domains. Each of the rows is one of the phenomena. We've got the human, so the distribution of human responses. Basically, in all of these, we want to see them rating what the literature says is the stronger argument. We want to see them rating it as stronger. So basically, if they're on the right-hand side of the graph, they're correct. And then GPT 3.5 is the green ones, and then the red is the single, or in sometimes discrete response. The reason that there are sometimes differences for GPT-4 is, remember, we're asking it for every single category, so there's actually a lot of questions. So it's summed over all of them. But what you can see is for all the ones that, again, I think of as about representation or similarity, pretty much GPT-4 does a pretty good job. GPT-3 is really very bimodal and less consistent. And we can actually capture that by just looking at, so for everything, we just did a kind of sign rank test comparing, is it on the right side or on the correct side, right? So you can see the humans, basically, we replicated the finding. All of the human responses said, the thing that was in the literature as being stronger, the human said was stronger. GPT-4, for the most part, did as well. And for GPT-3, it did not, right? For monotonicity, you see something very similar, where basically humans, again, in our data set, they showed, especially for general monotonicity, specific was a little raggedier, but in the right direction. GPT-4, again, replicated. This time GPT-3 did as well. But the most interesting thing, the least interesting thing is diversity. The reason this is least interesting is that our humans didn't replicate it, which it is a more fragile phenomenon in general, but I suspect this is because what we were doing is we were showing everyone sort of things from all three domains at once, and diversity is within domain. And since you've seen things from every domain, any small differences in diversity within domain are too small for humans to sort of reflect in their usage of the scale. I suspect that's what's going on. But either way, humans didn't show it, and neither did the models, although GPT-4 did a little bit. So I'm just going to park that there and pretend it didn't happen. And the last bit I want to talk about is non-monotonicity. And again, you probably anticipated that this is the one that GPT-4 did badly. The interesting thing is that it's not just, so GPT-3 just sort of, it's not just that they sort of didn't do it, it's that they actually showed the opposite thing very, very resounding and consistently. So essentially, they're applying monotonic reasoning all the time when humans apply non-monotonic reasoning. So, humans say it should tighten with more premises, or it shouldn't tighten with more premises, but the GPT-4 and 3 are saying otherwise. Except birds, general, I have no idea what's going on there. But other than that, that's a sort of fairly consistent pattern. So taken together then, what we have is this effect where, again, GPT-4 did much better than GPT-3 and than that we were expecting. But we still got sort of this interesting difference in performance on non-monotonic reasoning. Let me look at my timing here. Okay, I have time to talk about. So we did a little follow-up in experiment 2, where this time, instead of looking at all the phenomena, what we really wanted to do is try to tease apart how much is due to representation and how much is due to reasoning. So this time we got people to rate both, single arguments on a rating scale, and either the arguments had 2 premises or 1 premise. And we basically generated some random double premise arguments in a complicated generation process that tried to sort of capture the representation, really capture the space and blah, blah, blah. And then all the specific single premise arguments corresponding to that. So the reason that this is useful is that we could then compare the performance of humans with the various GPTs and also the similarity coverage model, which is a bespoke cognitive science model that captures this sort of reasoning. And we could also give the similarity coverage model the similarity representations extracted from GPT to see how, whether it was the reasoning with those or not that helped or hurt. And again, lots of prompt engineering is basically the same kind of thing as before. We're putting on the best results. And what you see is essentially that there's not a hugely consistent pattern, but more or less, the GPT-4s do about as well as humans do. So basically what I'm showing here is the Spearman correlation between humans to humans. So the split half reliability is the gold standard in a sense, right? That's that light blue bar. And the different colors are either the GPT or the sort of representations extracted from it with SCM using those. And human SCM is using human similarity representations and making the predictions SCM over those. So essentially what you see again is, all of them actually do pretty well and are about as reliable on the sort of specific kinds of arguments. Probably GPT 3.5 is the worst, but it's all reasonably good. It falls down a lot more for general ones. So these are the ones with conclusions that are like all mammals or all birds or whatever. But again, there's not a hugely consistent pattern. Like sometimes, like for vehicles, GPT 3.5 did extremely well. And humans actually have a hard time, the split half reliability for humans is also a lot noisier too. So yeah, it's hard to know exactly what to extract from this other than, GPT again did a surprisingly good job. And it's not just the case that if it's doing badly above, it's because its representations are wrong or something. Yeah. So yeah, short term, I'm going to conclude with some smaller conclusions and then some, because this is a workshop and I can blather on and you're trapped here with me. I'm going to give you some larger thoughts too. So The short-term conclusions, a big duh. GPT-4 is a lot better than GPT-3. Probably because of things like it's got a much larger short-term memory and it's got this image grounding. In particular, I think the image grounding sort of helps a lot with this kind of category induction problem, which probably uses, stems from some of our own visual representations. We also find that some of these phenomena themselves are more or less robust, again, which is consistent with some of the other research. Worth remembering, I didn't really get to go into the domain differences here, but there's really, humans do weird things with birds. I think it's actually due to expertise, like most, these were mechanical Turk people. And, if they're anything like me, the representations of birds are actually really fairly shallow and, it might reflect that, but just flag that. But I think, again, the most interesting thing is that the large language models really struggled with non-monotonicity, and not just in a way that they were in chance, but in a way that they actually made the opposite predictions very consistently. And the reason I spend all that time talking about sampling and data generation is that I think that is probably part of what's going on. And the reason I think this is part of what's going on, I'll talk about in my wider thoughts there. But essentially, it sort of captures, I think, what a lot of other people have said, which is, large language models are good on things that sort of have something to do or can be extracted from, like, predicting text. But if it requires larger theories of the world, in this case, something about sampling, but, also theories about causation or physical movement or whatever, that's where they stumble. And I think this is a similar issue. They also, in general, had a harder time with general arguments. And I think that's probably because the training really tries to get them not to hallucinate, like to go super far beyond the data, which often serves them well, but for general arguments, we actually want them to, right? And so they're more unwilling. Again, that's kind of a guess. So yeah, I feel like these are all pretty tentative conclusions and tentative results, but I think this is sort of lines up with the view we're seeing in a lot of other places that, large language models lack some of this kind of theory or grounding that people do. But then the sort of, so now I'm going to take a step back. And because I was thinking about, okay, what does this say about large language models, or maybe AI in principle and in theory? And I was struck by the fact that a lot of the ways that we study this involves basically giving the large language models tasks or queries, right? And then we compare the output with humans. And I think this obscures a real strong difference that I haven't seen many people talking about, which is, I think, quite evident in another excerpt from this little chat between my 7-year-old and ChatGPT. So this was his first question. And, I was off tidying, so I was not, here for any of this. I saw this all later. And he says, what do you do when you're not being used? And ChatGPT says, I'm not conscious or aware, blah, blah, blah. Kid says, sad. And the kid says, I don't feel, or, ChatGPT, I don't feel emotions. And the kid says, sad. And I'm not trying to be poetic here, although I think there is a poetic thing about this. But the fact that I think we have emotions has real implications for our actual cognition that, as cognitive scientists, it's really easy for us to overlook. And the implication is this, which is that emotions are basically information, a certain kind of really not very granular information, but they're information about actions that we should take in the world, right? Fear means you should flight, shame means you should hide, blah, 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 right? And we are agents in the world because we're driven by our emotions. And what that means is that as learners, unlike LLMs, we sort of actively seek out certain kinds of data. We only pay attention to some data. We're trying to sort of test and resolve hypotheses. And I think LLMs kind of implicitly do that, but they basically sit there and wait until they're given something. And that probably has really different implications for what we do with that data. And I think the whole idea of being attuned to the generative process is related to that, right? I'm seeking out data, so I'm always asking, where did this come from? Do I use this? And so forth. And again, you can see this in this little dialogue, right? So this is my kid. And so this was his second question after the emotions. So do you have superior technology? Blah, blah, blah. As an AI, okay, I'm not going to read, and now he goes on, and you can really see him. He is doing this. He is forming hypotheses about what the heck ChatGPT is. And I've never said anything. I've not, all I said was, here's a computer friend you can talk to, right? And he knew it was a computer. But he's sitting there doing the exact same thing we do. What's the weirdest word you can think of? What's that word mean? Like, can it make up stuff? He's asking. Now he's saying, can it answer me in this not terribly long-winded, annoying way, and he's saying, say 4 random things, put them in sentences. Like, he is actively exploring, the world, generating hypotheses about what AI does, make up 5 words, put them in an anagram. He found something that it couldn't work on, and he said, you got some words wrong, try again, right? And so this is sort of humans as a very active agent problem solver, not trained, that, I don't see, LLMs, again, I'm not saying in principle they can't, right? We know somewhat how to build models that seek out information and stuff, but right now they're not doing that. And I think that shapes their cognition in a deep way. And it's also questionable whether we should, like, I'm not worried about the singularity, but partly because LLMs have no agency. And once they do, I don't know. But I do think that it's worth thinking about what that lack of agency means for cognition. All right, that's it. Yeah. We have time for a few questions.
If you go back to the thought where you feel like humans comparison of like stronger arguments versus weaker arguments and
yeah, this one.
Yeah, I have a hard time understanding this thought. Maybe I missed something. Why is 2D for only those thoughts?
So it's only showing bars because it only gives discrete responses. So you can't get a probability distribution over it. So yeah, so this was sort of, we asked it to sort of basically, the prompt was they had to pick on a scale of A is much stronger, stronger, slightly stronger, whatever. So basically the potential bar locations correspond to those 3 places. Yeah.
Will this therefore give like a unfair advantage of 2D4 over 2D3.5? Because you're claiming that 2D4 is doing better, but it cannot predict like a continuous probability.
Well, yeah, except that all the statistics was basically just a sign, sort of, is it on the right side? So I don't think that actually advantages either sort of, discrete or continuous over the other. And that was pretty much what we cared. So, I'm not really fussed about where it was on the side because there's so much noise there. So yeah, I don't think that there's a worry about that. All right. Good question though. All right, I'm going to go back there and then, yeah.
Thanks for the very interesting talk. About the last point.
Yeah.
So,
sorry, I don't know why our language overlords don't want us to sort of, yeah. Yeah.
I think maybe one of the last barriers is to achieve agency, or if you want to or not. So one thing I'm kind of curious if you have thoughts about how can we tell if it achieved agency? It seems like such an intrinsic process.
Yeah. Well, I mean, I feel like the way that we can tell with humans when they achieve agency is they don't sit passively and wait for things to happen for them to do things. Again, this is why I'm not sure we want, but like, so essentially, and again, I know there are models that can sort of say, here's the thing, search it, like we have models of information search and everything, but they're not really incorporated into LLMs. So, once you've got a model that essentially has its own goals, and makes its own decisions about what actions to take rather than sort of responding to us, I would call that agency. Again, not sure we want to go there, but yeah.
Yeah, a bit following that question. We could, I believe, program it to feel emotions. Like in these situations, you are feeling fear.